First, thanks to the organizers for the opportunity and my confidence of my colleagues at the University of Kentucky for the putting me forward for the opportunity to talk to you today about work we're doing in my lab related towards developing a safer fentanyl derivative. So as probably many of you are aware of, this is a penny, and this is a lethal dose to a naive individual from someone dealing with fentanyl. And so predominantly that comes about as a result of the actions at the opioid receptor. So just some quick background, opioid agonists have been the mainstay for pain treatment for hundreds of years. They can be broadly classified into full agonists, partial agonists, and mixed agonist-antagonists, and part of this comes in dealing with some of their degree of selectivity for some receptors versus another. They exert their effects for the interaction with opioid receptors, in this particular case, namely being mu, delta, and kappa. And pain relief is predominantly mediated, at least in clinically used narcotics, for their actions on the mu opioid receptors. Now, chemically, opioids can be divided in three broad classes: opiates and their derivatives. So these are things derived from raw opium. Peptides, which are sort of the endogenous ligands for opioid receptors. And the last are going to be synthetics. Now, all opioids have major problems, and so while even though we think of them in terms of their negativeness, and certainly as a result of the opioid epidemic, they are essential for the effective practice of modern medicine. And from a clinical perspective, there's three major issues associated with opiates, namely tolerance, which means that you have to escalate the dose to produce the same level of effect. Constipation, which is part of the reason that you actually turns off the bowels, which is why opioids are used for the treatment of constipation. And lastly, respiratory depression, which is how people die from an overdose of this particular case. So morphine, which is extracted from the Papaver somniferum through the structure of medicinal chemistry, was simplified into structure by Paul Janssen and colleagues into the structure of fentanyl. And by doing this, they end up with a compound which is somewhere between 50 to 100 times more potent than morphine. And so both morphine as well as fentanyl exert their actions on opioid receptors. And when we think about sort of the greenness is when the opioid interacts with the opioid receptor, you produce analgesia. And the negative side effect, by also interacting with the same receptor, it produces the red, which is actually that of respiratory depression, which is how we do have a rescue agent, which is actually naloxone and related compounds, which actually do and reverse some of the respiratory depression seen with opiates. When somebody gets rescued from an opioid overdose, it's because they get an admission of naloxone or related compound. So you've probably seen this slide in other aspects. So this actually just shows you the rise, at least in terms of prescription opioid deaths in this particular fashion, which you can see it actually the sort of the rise here for any opioid. And certainly we can see in purple the rise here of synthetic opioids, namely fentanyl and or related compounds like tramadol. And so what the statistics show is that unfortunately is that we either need better opioids that are safer, or certainly we need better rescue agents. And so we started efforts in my labs to try to address that in this fashion. And so in essence, trying to develop an opioid antagonist or a better version of naloxone that might be more effective in the treatment of overdose, we actually did the exact opposite, where we identified a compound that was actually as potent, if not more potent than fentanyl as an opioid agonist. And this resulted in an entirely new class of opioid agonist. And so we're at first very upset, because this is certainly not what we set out to do in the first place, but sometimes you just have to make lemonade out of squashed lemons. And so we pushed forward. And so what this slide shows you here is that we initially profiled a compound which we termed atoxafant, which is in blue, comparing it to fentanyl. And I realize these numbers are kind of small. And the main take-home message here is down here on the bottom, is that atoxafant has a different molecular profile compared to other standard opioid agonists, namely that of such as morphine, fentanyl, and buprenorphine, which is predominantly used as an analgesic, as well as also that for the treatment of opioid abuse. So with this in hand and a further research compound, PZM21. We then looked at is we then wanted to profile this compound in animals. And so we did that, showing you once again the same color coding. What you can see is at least atoxafant in blue is about 10-fold more potent than morphine, which is actually not quite as potent as fentanyl, as you might imagine, but clearly it has an antinociceptive or analgesic effect in animals. And this differs from that of buprenorphine, which is widely known as a opioid partial agonist, which is used clinically for the treatment of both pain as well as an opioid use disorder. So we're getting a better level of analgesia with our compound compared to that. First bit of differentiation for our compound compared to that, actually, in terms of that, is actually looking at atoxafant, which is in blue as well as that of fentanyl in red. And this is a duration of action experiment, at least in mice, I should mention. And so what this is showing you is that the half-life, at least in terms of a duration of analgesia for atoxafant, is considerably longer, on the order of approximately 6 to 8 hours, compared to, at least in mice, fentanyl is about 1 hour. Now, I'll tell you in humans, at least in terms of the half-life of fentanyl, is on the order of about 6 to 8 hours in humans. And so there's certainly a species difference, but if one does a similar calculation, you would have an all-day acting analgesic of considerable potency with this compound. So realizing this might not necessarily be a problem, and so I should say that we compared these two at an equally analgesic dose, which is about tenfold compared to the mice. We then looked to see if you could actually reverse the antinociception or analgesia activity of that of fentanyl as well as our atoxaphant. And we can see in that you can reverse this particular case, indicating at least that the antinociceptive or analgesic actions associated with atoxaphant are the direct result of interaction with opioid receptors in vivo because of the reversal by the selective opioid antagonist naltrexone. And so this also shows, at least in terms of in similar aspects, that there appears to be a little bit more sensitivity to fentanyl compared to that, indicating that at least perhaps the mechanism of our compound atoxaphant is not the same as actually that of fentanyl. Now, our key slide here showing you this actually has to do with respiratory depression. So there's lots of ways to measure ventilation, which is a measure, at least in terms of respiration. So what this compound is showing you is that this is a lethal dose of fentanyl in this particular fashion. And we go to 10 times the dose and never relieve the same level of respiratory depression. So in essence, what we've shown here is that we have an opioid agonist which doesn't produce the same respiratory depression compared to fentanyl. And this, in terms of straight numbers, you get about a 70% reduction relative to fentanyl and only 45% for our compound, indicating that this particular compound has the potential to produce analgesia in humans without the production of respiratory depression, which would alleviate one of the three major problems I said in terms of opiates. So hopefully I've convinced you that our results have strong evidence that atoxaphant is pharmacologically different than other prototypical opioid agonists, in that it affords robust analgesia and long-acting analgesia tests. And we've recently described this in a paper in the Journal of Medicinal Chemistry, which better highlights some of the studies that we've done related to this particular presentation. Now, in terms of market, atoxaphant is a prototype of a new class of potent synthetic opioid agonist with the potential to replace fentanyl and all other opioids. Potential applications are in pain and opioid use disorder. So the global opioid market for that is about $22 billion a year. It's expected to go up about 1.4. If we look at substance use disorder, it's about $13 billion as well. And at least if we look at the opioid use disorder market, it's about somewhere about $4.5 billion a year. So there potentially is a large market for this. So in terms of next steps, we have filed a provision and patent application in 2003. We currently have a PCT application in preparation for both composition of matter and methods of use. So additional preclinical studies of what we're going now is we're going to looking at whether or not atoxaphant produces vocal cord closure and wooden chest syndrome, something that's been seen similarly with fentanyl. And so therefore we theoretically replace for all things in terms of fentanyl if produced in the case. We're also looking at least in terms of more abuse-related aspects of whether or not it produces less respiratory depression and certainly whether or not it produces withdrawal. So our commercialization plans or potential startup with Venture Studio, also looking potentially for investment, at least in terms of licensing with this particular compound. And the last thing is I don't work alone. And so lastly, I just like to know is that I'm a card-carrying, practicing medicinal chemist. I make all those inactive compounds. And then Jill Turner is my colleague who did all the mouse work related to that. Mike Bardo did the rat work, which showed, at least in terms of respiratory depression. And we have a breathing expert, Warren Elaine, who's involved with that. With that, I thank you very much for your attention. I'm very happy to answer any questions you may have.
Questions?
I couldn't get it from the slide, but what is the selectivity among the receptors?
So selectivity, it's about 1,000-fold or more compared to kappa receptors. It appears to be roughly activity in terms of a mu agonist, delta agonist, and it has no activity at all at the nociceptin receptors, sort of that fourth opioid receptor-like. So indicating.
I may have missed this, but with the much longer half-life, how would you predict that would affect tendency to become addicted to this substance compared to earlier?
Well, it's a great question. I think at least in terms of obviously with half-life then and staying around longer, then theoretically the effects are going to be around longer. So you're going to be less likely to seek drug seeking would probably be a case in terms of, so if we want to look in terms of addiction, whether it's in terms of drug seeking and or reward. And so certainly having a longer compound, it certainly has effects, at least with the potential for opioid use disorder in terms of a sort of a better, buprenorphine. I think at least in terms of pain, you certainly wouldn't have to dose as long in this particular aspect. And certainly, I mean, this is in a mouse, all right? And certainly with species difference, it's a lot to say that whether or not that mark actually would hold up in humans is somewhat case. I can tell you though, in terms of the pharmacokinetic aspects of this aspect, the compound is in the brain and accumulates in the brain and certainly over 4 hours. So all the effects that you see related to this are all centrally mediated.
Thank you very much.